Hello everyone. Today I want to tell you the story of Lake Urmia in northwest Iran. This is not only a story about a lake drying up, it is a story about how slow natural changes over thousands of years set the background and how very fast human water use in just a few decades pushed the system into crisis. Lake Urmia sits in northwest Iran. It is surrounded by mountains. It is a special type of lake called a closed basin. That simply means rivers flow into it, but no river flows out to the sea. The only way water leaves is mainly by evaporation into the air. Most of the water comes from 8 mountain rivers. The largest are Zarine and Simine on the south side. Ajicha is important on the east side. Others include Qadar, Mahaba, Shahrchai, Nazlu, and Baranduz. Because the lake has no outlet, its water level is like a simple water budget. If inflow from rivers and rain is bigger than evaporation, the lake rises and spreads. If inflow is smaller, the lake falls and gets saltier. If you look at satellite images from the 1990s and compare them to the 2020s, you see a shocking change. In the 1990s, Lake Urmia is a large, continuous body of water. In recent images, the shoreline has pulled back, huge salt flats are exposed, and the lake is split into pieces. So the big questions are, is this just another natural dry phase like ones the lake had in the past, or is it something different? To answer that, we need to look deeper in time. Over the last 2.6 million years, Earth has gone through many ice ages and warmer periods. Geologists call this time the Quaternary. During the colder Ice Age climate, strong erosion and winds in the surrounding mountains produce a lot of fine dust. Winds and rivers carry this fine material into the Lake Urmia basin, where it settles on the bottom together with mud, shells, and salts. Scientists drill long cores of mud from the lake margin. These cores are like a layered history book. Deeper layers are older, upper layers are younger. Inside each layer, they count tiny grains of pollen. Pollen is the yellow dust that plants release to reproduce. Different plants produce different pollen shapes, so under a microscope you can tell which types of plants were growing around the lake. The pattern that comes out is this. In some layers, steppe and semi-desert plants like artemisia and salt-tolerant shrubs dominate along with more gypsum and salt, which point to a lower saltier lake under drier conditions. In other layers, pollen from trees and wetlands such as oak, juniper, pistachio, and marsh plants appears with fine, organic rich mud and fewer salts, which point to a higher, fresher lake under relatively moisture conditions. One clear example of a dry phase is the Middle Holocene, about 5.5 to 4.9 thousand years ago, when the record shows a lower lake under drier conditions without large modern dams or pumps. This history gives us a natural variability baseline. It shows how much and how fast the lake level changed when climate and only small-scale human land use were in control. We use that range as a reference to compare with the recent crash. Another way to read the story is to look at the type of sediment near the old shorelines. First, coarse layers that are rich in evaporite minerals like gypsum and salt mark times when the lake was low. The water retreated, the shore moved past the coarse side, and evaporation was strong. Second, fine, dark, organic, rich mud marks times when the lake was deeper and the coarse side was well underwater. More algae and other life settled on the bottom in those wetter phases. On top of that, scientists measure magnetic properties of the sediment. These magnetic signals shift between low lake layers and high lake layers. That gives an extra cross-check. If both the visible sediment and the magnetic data tell the same story, we can be more confident about which times were wet and which were dry. When you combine the pollen record with these lake margin layers and magnetic clues, one message is clear. For thousands of years, Lake Urmia rose during wetter climate phases and fell during drier phases. Climate was the main driver, and it changed slowly. Now we jump forward to the last few decades. Today we have much more precise tools. Satellites watch the lake surface every few days. Other satellites sense changes in gravity that reveal changes in total water stored in the ground. When researchers put the modern record next to the long core record, they see that the recent drop in lake level is much steeper and much faster than typical natural swings. So climate is still important. It sets the background, how much it rains, how hot it is, how much snow the mountains get, but something extra must be pushing the lake down harder and faster than before. That extra push comes from human water use. What satellites show? First, we look at the lake surface. Satellite images from the late 1990s to the present show a steady loss in surface area and a big drop in shoreline. It's a strong downward trend. Next, we'll look at something called total water storage or TWS. TWS is a simple idea. It is all the water stored in basin put together. That includes the lake water, river water, soil moisture, or groundwater in aquifers. Special satellites called GRACE can sense tiny changes in Earth's gravity that happen when large amounts of water are added or removed. Over the Urmia basin, the GRACE data show that TWS has been falling. That means the whole basin is losing water, not only the lake surface. Groundwater and moisture are declining too. So we know two things. The lake is shrinking and the hidden water underground is also being drowned down. Why rivers fell more than rain? If this were only climate, you would expect a certain pattern. If rainfall drops by a little, say 10 or 15%, river inflow should also drop by roughly that amount, and evapotranspiration, which I will define in a second, should also decline. Evapotranspiration, or ET, is just a combined word for two things: evaporation from soil and water surfaces and transpiration from plants. In a natural dry spell, soils dry out, plants have less water, and ET usually goes down. What scientists actually see in the Urmia basin is different. Rainfall has decreased, but not dramatically. River inflow to the lake has decreased much more, often by half or more. Evapotranspiration has stayed relatively high, especially over irrigated land. This tells us that extra water is being supplied to the land surface beyond what rainfall alone would provide. The most straightforward explanation is irrigation. In other words, we are keeping fields green by diverting and pumping water. And that water is going back to the atmosphere from crops, not to the lake. What happens on farms? Let us zoom in on irrigation and farmland. Over recent decades, more land around Lake Urmia has been converted to irrigated fields and orchards. People grow wheat and barley, but also water-hungry crops like sugar beet, potato, alfalfa, apples, grapes, and other fruits and vegetables. To water these crops, several things happen. First, dams catch spring snowmelt on the rivers and store it in reservoirs. Second, canals carry that stored water to fields instead of letting it flow naturally to the lake. Third, when surface water is not enough, farmers pump groundwater from wells. On the fields, most of this water is used by crops and leaves the system as evapotranspiration. Only a small part seeps back to rivers, so the path of water has changed. In the past, water mostly went mountains, rivers, lake. Now much of it goes mountains, rivers, dams, canals, fields, sky. This is why river inflow to the lake has dropped much more than rainfall. The missing water is not a mystery. It is on our farms and then in the air. Groundwater pumping is another problem. Aquifers, which used to slowly feed rivers and the lake even in dry times, are being drained. So even when the weather improves, the base support for rivers is weaker. Climate versus human use, how models tested. Several research groups have tested this with computer models of the basin. These models keep track of rain, temperature, rivers, reservoirs, crops, and groundwater. In the figure, the black line is what we actually observe from satellites and lake data. The red line is a model run with human water use included, dams, irrigation, pumping. The blue line is a model run with the same climate but no human water use, only natural flow. In the climate-only run blue line, the basin dries a little, but not as much as in real life. In the climate plus human use run red line, the drop in stored water and lake level is much closer to the black observations. When only the run with human water use can match the real lake curve, it shows that dams, irrigation, and pumping are major drivers, on top of a drier climate background. This is what we mean when we say climate sets the background and human water use makes the fall much steeper and faster. The causeway. There is another human structure we need to mention, the causeway that crosses the lake. It's a solid embankment that splits the lake into north and south part. Water can only pass through limited openings. Most river inflow comes into the south part, so it is usually fresher and a bit higher. The north part gets less inflow and often becomes much saltier. When lake level is already low, the gap under the causeway becomes shallow. Also, mixing slows down even more. The north arm can turn into a very salty, shallow pond while some water still remains in the south. So the causeway is not the main reason the lake is drying. That is still too much water taken upstream, but the causeway makes the pattern of drying and salinity worse and more uneven. Lake Urmia is not just water, it is an ecosystem. The lake hosts brown shrimp called Artemia. These tiny creatures are a key food for birds such as flamingos and pelicans that migrate through or breed in the area. Artemia can survive salty water, but only up to a point. When salinity gets too high, they die off or become much less abundant. Birds then lose a feeding ground. As the lake retreats, large salt flats are exposed. Wind can pick up fine salty dust from these dry areas and carry it over farms and towns. People nearby may experience more dust storms, and there are concerns about effects on breathing and agriculture. So the drying lake means ecological stress and health and economic costs for communities around it. Thresholds and daily environmental flows. Because the lake is very shallow, small drops in level expose large new areas of the bottom. Scientists have identified some useful thresholds. For example, a lake level around 1274 meters above sea level is considered a rough target to keep enough surface area and moderate salinity. Below about 1269 to 1270 meters, small extra drops can expose a lot of new lake bed and cause sharp jumps in salinity. From lab and field data, researchers also know that Artemia and the bird community do best below about 1240 grams of salt per liter. Beyond that, the ecosystem becomes much more stressed. Water managers can work backward from these limits. If they know the lake shape and typical evaporation, they can calculate how much river inflow is needed each day to keep the lake level and salinity in a safe band. That required amount is called an environmental flow. It is simply the share of river water reserved for the lake and its ecosystem. It is important that these rules work on a daily scale, not only monthly averages. Slow melt comes in pulses that last a few days. If you block a big pulse with a dam and use almost all of it for irrigation, the lake misses a key chance to refill. Passing a fixed share of each daily peak is more protective and easier to monitor. WEAP and testing options. One common tool to test different water management options is called WEAP, which stands for Water Evaluation and Planning System. Think of it as a digital sketch of the basin. You draw the rivers, reservoirs, canals, cities, farms, and the lake. Then you give the model climate data and rules such as how much water cities and farms demand, how much water dams release or store, what fraction of flow is reserved for the lake each day. The model then simulates how the system behaves over many years. It reports how often users get their requested water, how often they face shortages, and how lake level and total storage change. This lets manager compare different scenarios. For example, what if we improve irrigation efficiency, or change cropping patterns, or enforce environmental flows more strictly? WEAP does not make decisions, but it shows the trade-offs. Putting all this together, scientists have explored future pathways. If water withdrawals continue as they have in recent decades, the lake stays low and very salty. Some wet years may give temporary relief, but the basic pattern does not change. If inflows are restored, irrigation is made more efficient and groundwater pumping is limited. Models suggest that partial recovery is possible. Climate change will likely add extra stress in the form of warmer temperature and maybe more variable rainfall, but water use remains the main lever humans can control. Key steps often suggested include 1. Reducing total withdrawals through better irrigation methods, less waste, and possibly shifting away from the thirstiest crops, especially in sensitive subbasins. 2. Restoring wetlands and river connections that help smooth flows and support both biodiversity and water quality. 3. Setting clear caps on groundwater extraction and enforcing them so aquifers can stabilize or slowly recharge. 4. Improving the causeway openings to allow better mixing between the north and south parts of the lake, especially during spring inflow peaks. 5. Agree on daily environmental flow that are treated like a non-negotiable water user alongside cities and farms. To pull the story together in simple terms, for thousands of years, Lake Urmia rose and fell mainly with climate. Wet phases with more trees and wetlands gave a higher fresher lake. Dry phases with more steppe plants and salt layers gave a lower saltier glacial lake. Those natural swings gives us a baseline. In the last few decades, the lake has dropped faster and farther than most of those natural swings. Satellite images, gravity-based water storage data, and hydrological models all point to the same conclusion. Climate made the background drier, but dams, irrigation, and groundwater pumping remove a much larger share of the water that used to reach the lake. The future of Lake Urmia is not fixed. It depends on choices. If upstream withdrawals keep rising, the lake will stay a shrinking, salty remnant. If inflow are protected, water use is managed more carefully, and environmental flows are respected, then a partial recovery is possible, even in a warming climate. That is the story I wanted to share, how slow ice age climate set the stage, how rapid human decision changed the script, and how science can help point toward a more hopeful ending.